introduction. And also thank you very much for inviting me to give a presentation here today. Okay, as you can see from my title, is the sound okay? Okay. I'm going to talk first about causality detection and then multi-scale decomposition of climate data, and then both with machine learning approaches. So first, causality identification. There we looked at two different approaches. One, convergent cross mapping and reservoir computing, and I will show you that they are very good for causality identification, and especially reservoir computing is also very robust against noise in the data, which is of course also something very important for climate data. And in the second part, I'm going to use machine learning, especially dynamic mode decomposition, to look how we can actually identify physically important patterns in high-dimensional climate data sets. Okay, I probably don't really have to say much about causality. That's, of course, something we scientists are very interested in, to see if we see some response, what's the actual cause. And of course, there is lots of things going on, and sometimes you might see some connection, some correlation between two variables. So here, for example, ice cream days and the number of shark attacks, where you might think there might be a relation, but that's of course just some simple correlation, doesn't necessarily imply causal relationship. So for this, we kind of have to use more sophisticated methods, since most of the correlation methods typically are only valid for linear systems with Gaussian noise. That's if you already have some nonlinear system, correlations could be misleading. Okay, first a little bit about convergent cross mapping, which was originally developed by Sugihara and co-workers, and that's based on Tarkin's embedding theorem. So that's based on the fact that, say, you have a high-dimensional system and you want to reconstruct the attractor. And Tarkin showed that basically you can just take one single observation variable, x, to reconstruct the full attractor. And there is then also that there is a mapping from the reconstructed or shadow attractor to the true attractor. And the property convergent cross mapping uses is basically if we have, say, two variables, x and y, which belong to the same dynamical system, that we can basically use x, or if we do the reconstruction and points which would be close to x at a certain time would also be kind of, the corresponding points would also be close to y in the alternative reconstruction. So the idea is now, if we can predict x on the attractor mx, that basically would tell us also something about the current state of y. And that's basically the idea of convergent cross mapping, so that we kind of can identify this also then with causal relationships, that, for example, x might have caused a change in y. So those cause and effect relationships don't have to occur at the same instant in time, and so there could be some delay. So for this reason, we basically we make the prediction, but also already with some lags ahead of time, or even maybe some lagged in the past. So we have then our estimated value, and then we can compare this with the measured or the real value, and then basically come up with some lagged CCM coefficient correlations between different time instances, and then identify this as the causal relationship, if also the lag relationship is properly. So I'm going to show you later on some examples where this probably becomes more clearer. So the other method we looked at is reservoir computing, which is a recurrent neural network. And that's also very attractive because it's actually relatively quick to train this network. So that's reservoir computing consists, as the name says, as a reservoir for mapping inputs into a high-dimensional space and some readout for pattern analysis from those high-dimensional states in the reservoir. But this reservoir is fixed. So that has the advantage that the training is actually relatively easy to do or relatively quick. And then we can train this using some linear regression to actually then map this, put basically our input x to y at also maybe at some different time lag. And again, those cause effect or response relationships don't have to occur at the same time. So basically we construct a prediction model if we put in A or X to predict then B or Y, and have a prediction model also for where we input Y to predict then the opposite variable X, for example. And then we have those, we can evaluate the predictive skill and then basically also compare different lags. So for variable to identify as the causal variable, basically we would expect a peak at negative lags, and the response would have a peak for positive lags. Now that's displayed here. So we look at this nonlinear system where we have here this nonlinear coupling where y is coupled to x, and then we also look at the second system where basically x and z are both coupled in both directions. So that would be unidirectional coupling, that's a bidirectional coupling. And then we have here reservoir computing on the top and convergent cross mapping on the bottom. Then we can predict, say, if we use x or y, that would be then the red or the blue line, to predict then the other variable. And we can see here that we have a peak for negative lag, so that would be the causal variable. And if we then see here a lag or the peak in the correlation for positive lags, so that would be then the response. So for different coupling strengths, those two figures here would then indicate that the red line basically causes, or basically X causes response in Y. So we have this peak here and the peak here, and also CCM produces relatively similar results. Then we can change the coupling strength a little bit, and with reservoir computing, we still see this causal and response effect very clearly. Where CCM, that's already the response becomes less pronounced. So probably is here this dashed line indicates the statistical significance. Everything below this dashed line is not significant. So here we still see the significant causal variable, but the response becomes insignificant. So that already indicates that reservoir computing might be more robust than CCM. And here with the bidirectional coupling, then of course we both variables are basically causing effects in the opposite variable, in the second variable. So we also see then basically that they overlap very clearly, and that's also the case for both methods. Then in climate data, we typically have a problem that we have to deal with noisy data. So we take those previous systems and then just artificially add some noise to the time series. And here we just compare different amounts of noise which we add. So that's here for reservoir computing, and we basically look here at the relative deviation, which is defined by this object. And you see, of course, if we increase the amount of noise, then the relative deviation increases. But here, reservoir computing has a much lower increase than CCM, convergent cross mapping. So that also indicates that reservoir computing is a much more robust method against noise than CCM, which is this phase-space reconstruction is known to be relatively sensitive to noise. Okay, so these were two relatively simple models. Then we also looked at a much higher dimensional model, a variant of de Lorentz 96 model, which is given here. So we have many more degrees of freedom. So we have, basically we have a kind of a circle of grid points. So it's basically a circular motion here. And then every xi also has interacts with much faster variables, those yij's. So that's something where we have lots of wave behavior. And then we can now oops, that was one too fast. Basically look at the causal and response relationship between not really nearby nodes, so to say, but also nodes which are kind of a little bit more distant to each other, and basically see how the cause, the effects basically propagate through those different nodes. That's what we display here again for reservoir computing and CCM. So we basically start with very close by nodes, so the legs are very close to each other, and if we then basically increase the distance, so we go from 1 to 2, 3, 4, and so, and also to different Y modes, then we also see that basically that the peak of those correlations here basically shifts, and also that basically the distance we would expect from here then with time steps kind of can be reconstructed using those lagged causal methods. Okay, that's the first part about causality detection. So I demonstrated that we can actually use machine learning to identify causal relationships, and we published this here in Chaos. The second part is going to high or much more higher dimensional data and trying to identify physically meaningful patterns with the so-called dynamic mode decomposition method. So in climate, we have high dimensional data sets. So we typically have a horizontal grid, maybe even with vertical extent, and then also the time dimension. So we could typically we have 4-dimensional data. Here I just concentrate on 3-dimensional data, and we basically see different anomalies propagating through the phase space, high dimensional, and try to identify which ones actually are kind of physically meaningful. So there are, of course, many methods we can use. One of the most well-known methods in climate research are empirical orthogonal functions. They are, of course, also very powerful, especially if we want to reduce the dimensionality of the problem. But then they also have some drawbacks. Say the EOF modes have to be orthogonal to each other. But of course, there is no reasons that the physical dynamics need to be orthogonal to each other for those modes. So DMD is also in this sense a dimensionality reduction algorithms. And the advantage is, especially also compared to EOFs, that for each mode we identify, we basically have an oscillation frequency and a decay growth rate. So, and especially if we would deal with a linear system, then those modes and frequencies would be analogous to the normal modes of the system. But DMD, at least the theory behind this, is much more general. So in principle, it can also deal with nonlinear systems because there is a close connection to the so-called Koopman operator. And so on one hand, DMD has the advantage it's not orthogonal in contrast to EOS, but then it might not be as parsimonious. Maybe it doesn't provide us with a as compact basis as EOF. So that's then depending more on the physical question we might have in mind. Okay, just some more mathematical background. So we have here our dynamic system. F would be a nonlinear function depending on the state variable x time and some parameters. And DMD allows us to basically approximate locally this with a linear approximation. And then we would have here the solution for x, basically those oscillation patterns, where we, of course, they're now complex patterns. So we have a real and imaginary part. So we have the oscillation frequency and growth or decay rates. So DMD approximates the so-called Koopman operator, and the Koopman operator is given here. So that basically gives us or allows us even to deal with or to approximate the nonlinear dynamics with a linear operator, but we would actually now deal in an infinite dimensional system. But of course, DMD, because that's data-driven, we only have a finite dimensional approximation of the Koopman operator. So a Koopman operator typically deals also with nonlinear observations, whereas here for DMD, we basically have to find the observations which would be suitable directly from the data, but then we can come up with this approximation, this linear approximation, and then basically easily compute those DMD eigenmodes. Okay, so we have here our data, so basic snapshots at different time instances. And from this, we can basically construct a data matrix, so X, and then we kind of shift this by a certain leg so that we have here also X prime. Then we can compute this product X prime X to get the matrix A, and then basically look at the eigenvalues and eigenvectors for this. And here we actually have quite a lot of freedom, which kind of time step size we use and over which period of time we do this. So one could, of course, use the whole time series we might have available, but then we might lose also some insight into the data. So standard DMD kind of requires us to make some decisions about such things. That's why we started looking at the so-called multi-resolution DMD, because in the climate system we have lots of interesting phenomena which exist on particular time scales. And also they might just appear very intermittently. So we kind of want to have a method which can also identify, say, intermittent patterns and look at different time scales. So and multi-resolution DMD would be one way of doing this. How does this work? So if this would be here our full time series, say 100 years or so of monthly mean data. So the first step would be to analyze the full time series. So then we look only at some low frequency modes. Say we look at those eigenvalues and only consider eigenvalues which would only allow for, say, 2 oscillations in this time period. Then we basically halve the time series in the first half, second half, and then repeat this. So then we already would look at somewhat faster dynamics than if we look only at the first step. And then we can just repeat this again. Each half will be halved again, And we just repeat this until we basically run out of data so that we can't have the data any longer. And then at each segment, basically, we can look at the corresponding frequency data and look whether we find some interesting dynamics or not. So to illustrate this, we looked at sea surface temperatures, we looked at the ERSST version 5 dataset, so that's monthly mean SST data from 1854 to 2020. So let's say the first level. So that would be the first DMD mode with eigen. So DMDs are normalized in such a way that the eigenvalues typically are very close to 1. So and here we only find eigenvalues, eigenvectors with only real components. So basically we have standing patterns, standing waves also. And the first pattern always looks pretty much like the climatological mean state, which is displayed here. And then we also looked how they actually correlate with those monthly mean SST values here. And then in the first mode or step, we also find two more patterns, which are displayed here. And here you can see that this one is pretty much constant as the first, but then here the second and third, you see some very ultra low frequency behavior a little bit. And you can see here then the changes that we have here, anomalously high SST temperatures, whereas then here in the polar regions, much lower temperatures. Then one nice feature is also that multi-resolution DMD can identify changes in the annual cycle. For here, we basically have to go down to the 8th level, and then we can look at the eigenvalues and see what kind of oscillation period of frequency they have. And so we can also see here or identify changes in variability in the annual cycle. So that we can then look here also at the different how those DMD modes look like here. So that would be the first, again, which has a real eigenvalue of close to 1. So that would be for this segment, it would be the 10th segment here if we go from those halves. So pretty much like those corresponding climatological mean or over this shorter period, of course, and this would be then basically the DMD mode corresponding to the annual cycle, which has also a period of about 12 months. And you can also see, so now we have a real and imaginary component. So now we could basically in principle reconstruct the evolution over this period of the annual cycle. And here you see the pattern correlations with the monthly means from the original data. And then here we see that the couple of times then we have anomalously long season cycles, but of course also when we have very short annual cycles, so we also computed composites over those periods, and you can also see here very distinct changes of SST values between long and short annual cycle events. Then looking at SST, one important property is, of course, with this method, can it also identify ENSO events? And here I just demonstrate this with the ENSO event of 1987. So again, we have a real and imaginary component, so that's also what indicate or provide us information about the evolution of the ENSO event, and also here with the pattern correlations. So, okay. So maybe a little bit more about this figure. So basically here we have the time series. And then basically here, this would be the first level, the full time series. Then we would have here the halves quarter, and basically up to very high frequency data. So basically, we can look at the output of the multi-resolution DMD to identify when we have periods of enhanced variability or decreased variability. Everything which is here pretty much yellow would have reduced variability, and everything more reddish would have increased variability. So we see here the longest time scale, we have increased activity, if we want to call it this way, and this would be here corresponding to the annual cycle. And then we can also see here very much other periods of time where we have active, say those DMD modes being active or less active. Yes. So, and then now we can just focus on this one, this point, or this period here. So that has some time scale of about 20 years. And here are the corresponding DMD modes. And so I would have expected to maybe see something more like the pacific decadal oscillation. I mean, maybe there is some indication of this, but there's not really a clear correspondence to those decadal SST patterns if we do this DMD decomposition. Okay, that was also published earlier this year in the Chaos Journal if you want to read more about this. And I come to my summary. So first I talked a little bit about causality identification with machine learning methods. So especially reservoir computing is very well suited for identifying causal links because it's also very robust against noise in the time series, and it's also relatively fast, also much faster than convergent cross mapping. And in the second part, I talked about multi-resolution DMD, how to identify physically meaningful patterns in high-dimensional data sets. And here I kind of emphasized that DMD might be very good in identifying changes in the annual cycle or just how the annual cycle changes, and also could be used or can also detect ENSO events, which I think is also just a nice property to have. Thank you very much for your attention, and I'm happy to answer questions.
Thank you very much, Christian. Questions? Yes, please. Maybe you can also say your name quickly. And there is a microphone. Maybe you can just come to the front.
Hi, I'm Dominik Safranek. Yeah, I was wondering, you started the talk with saying, oh, the correlation is not the same as causation. But through the rest of the talk, it seems to me that you already decided what's the source of the what's the cause of the other thing, because your models are trying to find some mapping, right? So you already knows what's the source of the second thing. You already decided what's X and Y. So I wonder about your conclusion. You said you identify causal links, but it seems to me that you decided what is the causal relation in the first place.
I mean, we of course test this with those methods where we know what the cause-effect relationship is in order to test whether we can still identify this by then just looking at the data. So we basically come up with those or construct those models, produce data, but then we just use the data and basically are able to reconstruct those causal relationships.
I see, but in the end, it's just a mapping, and the causal relationship can be identified using these machine learning methods, right? It comes from something else. Like whether it's causal or just correlation, that doesn't come from the machine learning. Do I understand that correctly?
No. I mean, the machine learning, those methods, I mean, they're basically only used to make predictions. So reservoir computing, I think, is very powerful for representing or predicting dynamical systems.
Right.
And we then just use this we basically claim if we can make successful predictions, that we can identify those causal relationships.
Okay, but at the same time, you could train it on the data of shark attacks and predict the number of ice cream sold, right? Yeah. Okay.
One could try to do this.
Thank
Uh,
you.
There was another question, Sergey?
Just a technical question, Sergey, flach my name. This DMD sounds to me a bit like similar to Lyapunov exponent calculation in, say, Hamiltonian, but maybe also non-Hamiltonian dynamical systems. Can you comment on that? How these DMDs are related to the linearization of the phase space flow around the trajectory in a standard nonlinear system?
That's a good question. I think I would need to think more about this to answer.
Thank you.
I have a related question. How do they differ from POPs?
They are very closely related. POPs, I mean, you could show, or some other people show that they're kind of a special case of DMDs. DMDs are just, in a way, much more general. So POPs, they're basically, you assume that, or you make this linearization of the system here. One can argue, because of the relationship to the Koopman operator, that we can still kind of identify also nonlinear signals or processes.
Okay. Yeah, I think we need to move on to the next topic, but feel free to contact Christian also afterwards. Thanks very much, Christian, again.